Imagine standing at the absolute edge of everything that exists. Behind you stretches all of space, all of matter, every galaxy and star that has ever burned. In front of you lies nothing, not empty space, not darkness, not even the concept of distance, just the end of reality itself. What would you see? What would happen if you tried to reach out and touch the boundary? The answer is far stranger than you can imagine, and it challenges everything physics thought it understood about the nature of existence. Hit that like button and subscribe as we journey to the most impossible place in the cosmos. Prepare yourselves. We begin. The question seems simple enough. If the universe has an edge, what's beyond it? But this innocent question contains a logical trap that has ensnared even brilliant physicists. The word beyond assumes there's something outside the universe, some larger space that contains it. But by definition, the universe is everything that exists. There cannot be a beyond, because the universe includes all possible beyonds. Asking what lies beyond the universe is like asking what's north of the North Pole. The question itself breaks down because it uses concepts that only make sense within the thing you're asking about. Yet our brains cannot help but imagine an edge. We've lived our entire lives in a world where everything has boundaries. Rooms have walls. Countries have borders. Even the observable universe has a horizon beyond which we cannot see. Every human experience tells us that things have edges, that there's always something on the other side. Breaking free from this intuition requires understanding that the universe might not work like anything we've ever encountered. Current cosmology offers three main possibilities for the universe's shape, and each one handles the edge question differently. The universe could be infinite, stretching forever in all directions with no edge whatsoever. It could be finite but unbounded, curving back on, itself like the surface of a sphere, so that traveling in one direction eventually brings you back to your starting point. Or it could be finite with an actual edge, though this option creates more problems than it solves. The first possibility, an infinite universe, eliminates the edge question entirely. If space extends forever, there's nowhere for an edge to exist. You could travel in any direction for eternity and never reach a boundary. This sounds like an escape from the paradox, but infinity creates its own disturbing implications. An infinite universe containing infinite matter means that every possible arrangement of particles must occur somewhere. There would be infinite copies of you, infinite Earths, infinite versions of every moment you've ever experienced, all scattered across the endless expanse. But the mathematics of infinity get even stranger. An infinite universe could double in size during cosmic expansion and still be infinite. Infinity times 2 equals infinity. The expansion we observe doesn't mean the universe is growing larger in some absolute sense. It means the scale factor of space itself is increasing, making distances between objects grow even though the total size remains infinite. This is expansion without an edge, growth without a boundary, a process that our finite minds struggle to comprehend. The second possibility involves a finite universe that curves back on itself. Imagine you're an ant walking on the surface of a balloon. You can walk in any direction forever without reaching an edge. The surface is finite. It has a specific total area, but it has no boundary. You never fall off or run into a wall. If you keep walking in a straight line, you eventually return to where you started. The universe could work this way in 3 dimensions. In such a closed universe, space curves in on itself through a dimension we cannot perceive or point to. Just as the balloon surface is 2-dimensional but curves through 3-dimensional space, our 3-dimensional universe could curve through a 4th spatial dimension. Travel far enough in any direction, and you'd eventually loop back to your starting point. The universe would be like a cosmic hall of mirrors, where light from distant galaxies could potentially circle the entire universe multiple times, creating repeating patterns in different directions. Current measurements of the cosmic microwave background, the ancient light from the early universe, suggest that space is either flat or extremely close to flat. A flat universe can be infinite, extending forever in all directions. But flatness doesn't guarantee infinity. You can roll a flat sheet of paper into a cylinder, or connect its edges to make a torus, a donut shape. The geometry remains locally flat, but the overall topology becomes finite and closed. Our universe could have this structure, finite in volume but with no edge to run into. The observations tell us that if the universe does curve back on itself, it must be vastly larger than the observable portion we can see. The observable universe has a radius of about 46 billion light years. If the universe was small enough to wrap around, we would see repeating patterns in the cosmic microwave background where light has traveled all the way around and returned from the opposite direction. No such patterns have been found. Either the universe is infinite, or it's so enormous that light hasn't had time to circle it even once during the nearly 14 billion years since the Big Bang. But what about the third possibility? What if the universe really does have an edge, a definite boundary where space simply ends? This scenario creates immediate logical problems. If space ends at some location, what happens to the laws of physics at that boundary? General relativity describes how matter and energy curve spacetime. But these equations assume that space extends smoothly in all directions. An edge would create a discontinuity, a place where the mathematical framework breaks down completely. Imagine approaching this hypothetical edge. As you get closer, you'd presumably see less and less matter ahead of you. Eventually, you'd see the last galaxy, the last star, the last particle. Then what? Would you see a wall, a barrier marking where space ends? How would such a barrier exist? What would it be made of? Would it be physical or just an abstract boundary? If it's physical, it's made of something, which means there must be space for it to occupy. If it's not physical, how does it prevent you from going farther? Perhaps the edge isn't a wall, but simply a place where the laws of physics cease to function. Beyond this boundary, the concepts of distance, time, and causality might have no meaning. You couldn't travel past it because past it doesn't exist. There's no space to move through, no time in which to move. This sounds like science fiction, but it's a logically consistent possibility. The universe could simply stop existing at some location with nothing, not even empty space lying beyond. But this creates a profound problem for the Big Bang model. If the universe began from an initial singularity and has been expanding ever since, what expanded into what? If there was an edge in the beginning, that edge would be expanding outward. But outward into where? The standard answer is that the Big Bang didn't happen at a point in pre-existing space. It happened everywhere simultaneously. Space itself expanded, carrying matter and energy along with it. There was no edge because there was no outside for an edge to border. Yet if the universe has an edge now, it must have had an edge then. And if space is created as the universe expands, that edge must be moving outward into something. Unless we're willing to accept that new space is constantly being created from absolute nothingness at the boundary, which raises the question of what mechanism drives this creation and why it occurs at this specific boundary rather than anywhere else. Some cosmological models attempt to address these problems by proposing that our universe is embedded in a higher dimensional space. String theory, for instance, suggests that reality has 9 or 10 spatial dimensions, but most of them are curled up so tightly that we cannot perceive them. Our familiar three-dimensional space might be a membrane floating in this higher dimensional bulk space. In such models, the edge of our universe could be a genuine boundary where our three-dimensional brain ends and the higher dimensional bulk continues. This framework allows for an edge without requiring something beyond it in our space. The bulk provides the larger container that resolves the paradox. Our universe could have a definite boundary in three-dimensional space, while being embedded in a larger, higher dimensional reality. If you could somehow reach the edge, you might not see a wall or experience a discontinuity. You might simply find yourself unable to continue in three-dimensional space because the directions you could move become higher dimensional directions you cannot perceive or access. But even this solution creates new questions. What prevents matter and energy from our universe from leaking into the bulk? Why does everything except gravity seem confined to our three-dimensional brain? And if there are other brains floating in the bulk, could they have their own three-dimensional universes, their own space and time, existing parallel to ours in directions we cannot point to? The most radical possibility is that the edge isn't a place at all, but a fundamental limit imposed by the structure of space-time itself. Quantum gravity theory suggests that space isn't continuous, but made of discrete units at the smallest scales. Just as matter is made of atoms, space itself might be made of indivisible quantum chunks, roughly 10 to the power of minus 35 meters across. This is the Planck length, the scale where quantum effects of gravity become dominant. If space is fundamentally discrete, then asking what lies beyond the edge might be like asking what lies between atoms. The question assumes continuity where none exists. The universe could have a finite number of these spatial units, and that's all there is. No edge, no boundary, just a finite collection of discrete elements of space with no possibility of more because space itself is quantized. This idea connects to the holographic principle, one of the most profound insights in modern theoretical physics. The holographic principle suggests that all the information contained within any volume of space can be encoded on the surface that bounds that volume. Just as a hologram encodes three-dimensional images on two-dimensional film, the universe might encode all its information on a two-dimensional boundary. If the holographic principle is correct, then the universe might not be what it appears to be. The three-dimensional space we experience could be a kind of projection or emergence from information encoded on a two-dimensional surface. In this framework, asking about the edge of the universe becomes asking about the limits of this informational encoding. The edge wouldn't be a place you could travel to, but rather a fundamental boundary in how much information can be encoded in the cosmic hologram. But perhaps the most mind-bending possibility is that the edge of the universe moves with you. This sounds absurd, but it follows naturally from the expansion of space and the finite speed of light. The observable universe, the region from which light has had time to reach us, has a boundary called the cosmic horizon. Beyond this horizon lie regions of space that are receding from us faster than light can travel through the expanding space between us. This horizon isn't fixed. As time passes, light from more distant regions reaches us, and the observable universe grows. But accelerating cosmic expansion, driven by dark energy, means that some galaxies will eventually cross the horizon in the other direction. As space expands faster and faster, these galaxies will recede so rapidly that their light can never reach us again. From our perspective, they will fade away and disappear, crossing an event horizon not unlike the boundary of a black hole. In this sense, Every observer in the universe lives at the center of their own observable bubble. The edge of this bubble, the cosmic horizon, is unique to each observer's location. If you could somehow travel to a galaxy near your cosmic horizon, you'd find yourself in the center of a new observable bubble with a different horizon. The edge would have moved with you. This creates a strange picture of the universe. Every location is surrounded by its own horizon, its own edge beyond which that observer cannot see. The universe could be infinite, but every observer experiences it as finite and bounded. The edge exists not as an objective feature of reality, but as a consequence of each observer's limited vantage point in space-time. Here's what makes this truly unsettling. Because of accelerating expansion, the observable universe is actually shrinking in terms of what we can causally affect or be affected by. Galaxies that we can see today will eventually cross our horizon and disappear forever. In the far future, observers in our galaxy will see a universe that appears much smaller and emptier than what we observe now. Their edge, their cosmic horizon, will be closer than ours. Eventually, only our local cluster of galaxies will remain visible. Everything else will have receded beyond the horizon. Future astronomers will observe a universe that appears small, static, and eternal. They will see no evidence of cosmic expansion, no cosmic microwave background, no hint of the Big Bang. The edge of their observable universe will encompass only a few dozen galaxies surrounded by apparently infinite empty space. If you tried to reach this edge by traveling toward it, you'd never arrive. The horizon is defined by light's travel time through expanding space. As you move toward it, you'd find that galaxies previously beyond your horizon would come into view, while galaxies behind you would disappear beyond the opposite horizon. The edge would always remain the same distance away, measured in light travel time, because it's defined by the relationship between expansion and light speed. This is similar to trying to reach the horizon when you're standing on the Earth's surface. No matter how far you walk toward the horizon, it remains the same distance away, because it's not a place, but a consequence of your viewpoint and the planet's curvature. The cosmic horizon works the same way, except it's determined by the expansion of space rather than geometric curvature. But what if you could somehow exceed the speed of light? What if you could jump ahead faster than the expanding space recedes? Relativity tells us this is impossible because nothing can move through space faster than light. But relativity doesn't forbid space itself from expanding faster than light. And hypothetically, if you could move through space faster than light, you could in principle reach regions that are currently beyond your cosmic horizon. If you did this, you wouldn't reach an edge or boundary. You'd simply find yourself in a new region of space that looks statistically similar to your starting point. More galaxies, more structure, more of the same kinds of things we observe locally. Current cosmological models suggest the universe is homogeneous on the larger scales, meaning it looks roughly the same everywhere when averaged over sufficiently large volumes. This homogeneity is one of the strongest arguments against an edge. If the universe has an edge, we'd expect to see evidence of that boundary. Galaxies near the edge would experience different conditions than galaxies far from it. We'd see gradients in structure, density, or composition as we looked in different directions. Instead, observations show that the universe looks remarkably uniform in all directions. Every direction appears equivalent, suggesting that either there is no edge, or we're so far from it that its effects are undetectable. There's another way the universe could have an edge that's stranger than anything we've discussed. What if the edge exists not in space but in time? The Big Bang represents a temporal boundary, a moment before which time itself might not have existed. If you could somehow travel backward in time to the Big Bang, you'd reach an edge not of space but of time itself. There is no before the Big Bang because before requires time, and time began with the Big Bang. This temporal edge is in some ways more fundamental than any spatial edge. No matter how the universe is shaped spatially, whether infinite or finite, flat or curved, it appears to have a beginning in time. The cosmic microwave background provides a snapshot of the universe when it was only 380,000 years old. Before that moment, the universe was opaque to light. Before the first second, the universe was so hot and dense that our current physics cannot describe it. Some theories suggest that the Big Bang wasn't the true beginning, but rather a transition from a previous state. Cyclic models propose that the universe undergoes endless cycles of expansion and contraction, with each Big Bang emerging from the collapse of a previous universe. Eternal inflation theories suggest that our Big Bang was just one bubble nucleating in a larger eternally inflating space, with countless other bubbles creating their own universes. But even these models don't eliminate the edge problem. They just move it to a different level. If the multiverse is eternal, what initiated the eternal inflation? If the cycle of universes is endless, what started the cycle? Either there was a true beginning, an ultimate temporal edge, or reality extends infinitely backward in time, creating logical paradoxes about infinite regress. The edge question also connects to one of the deepest problems in cosmology, the horizon problem. In the early universe, regions of space that are now on opposite sides of the observable universe were so far apart that light couldn't have traveled between them. They were beyond each other's horizons. Yet when we observe the cosmic microwave background from these causally disconnected regions, we find they have almost identical temperatures. How did regions that could never have communicated end up with the same properties? The standard answer is cosmic inflation, a brief period of exponential expansion in the universe's first fraction of a second. Inflation stretched a tiny region of space that was small enough to be in thermal equilibrium to a size larger than our current observable universe. The regions we now see in opposite directions were once close enough to exchange energy and reach the same temperature. But inflation doesn't truly solve the edge problem. It just pushes it to a different scale. If inflation expanded a small patch of space to create our observable universe, what lies beyond that patch? Is there an edge to the inflated region? Or does inflation continue forever, creating infinite space filled with infinite bubble universes, each with its own physics and properties? Current observations cannot distinguish between these possibilities. We can only observe our local bubble, our inflated patch. Everything beyond our cosmic horizon remains speculation based on theoretical extrapolation. The edge, if it exists, lies forever beyond our ability to observe it directly. This brings us to a profound realization. The question of whether the universe has an edge might be fundamentally unanswerable, not because we lack sufficient technology or observations, but because the very nature of cosmic horizons prevents us from accessing the information needed to resolve the question. We are trapped inside our observable bubble, unable to see what lies beyond our horizon, unable to determine if the universe continues indefinitely or ends somewhere. Some physicists argue that questions which cannot be answered even in principle aren't truly scientific. If no observation could ever tell us whether the universe has an edge beyond our cosmic horizon, then perhaps the question belongs to philosophy or metaphysics rather than physics. Others counter that the mathematical consistency of our theories requires answers to these questions, even if we cannot verify those answers observationally. The edge question also raises issues about the nature of scientific explanation. Throughout history, scientific progress has often involved expanding our perspective beyond what we can directly observe. We accept that atoms exist even though we cannot see them. We believe in the existence of black hole interiors even though no information can escape from them to confirm our theories. We model the cosmic microwave background coming from regions that were beyond our horizon when the light was emitted. In each case, we infer the existence of unobservable things because they're required by theories that successfully explain what we can observe. The same logic could apply to the universe beyond our horizon. Even though we cannot observe it directly, the mathematical structure of our best theories might require that it exists and has specific properties. But there's a crucial difference. When we infer the existence of atoms or black hole interiors, we're extrapolating from observed phenomena using well-tested theories. With the universe beyond our horizon, we're extrapolating far beyond any observational constraints. We're assuming that the laws of physics we observe locally continue to hold in regions we can never access. This assumption might be correct, but we have no way to verify it. What if the laws of physics change beyond our horizon? What if different regions of space have different physical constants, different particles, different forces? Some versions of eternal inflation predict exactly this kind of cosmic variation. Each bubble universe in the eternally inflating multiverse could have its own vacuum state, its own physics. The edge between different bubbles would be a transition region where the laws of physics themselves change. If this is true, then asking what happens when you reach the edge takes on new meaning. You wouldn't just leave our universe and enter empty space or nothingness. You'd cross into a region where reality operates by different rules. Matter might not exist in the same form. Time might flow differently. The fundamental constants that determine chemistry, nuclear physics, and gravity might have different values. Such an edge would be more radical than any physical boundary. It would be a boundary between different possible realities, different ways that the laws of nature could be. You couldn't simply walk across it, because the physics that allows walking, that allows coherent objects to persist, might not apply on the other side. This connects to the anthropic principle, the observation that we find ourselves in a universe compatible with our existence, because only such universes can contain observers to find themselves anywhere. If the multiverse contains bubble universes with every possible combination of physical laws, the vast majority would be sterile, unable to form stars, planets, or life. We necessarily observe ourselves in one of the rare bubbles where the physics allows complexity to develop. In this framework, the edge of our universe isn't arbitrary. It's defined by the boundary of the region where our specific physics applies, the bubble within the larger multiverse, where the physical constants have the values needed for matter to exist in familiar forms. Beyond that edge lies not empty space, but different physics, different possibilities, different realities, but we're still left with the fundamental question. If you could somehow reach this edge, what would you experience? The honest answer is that we don't know, because we don't have a complete theory of quantum gravity that could describe what happens at the boundary between different vacuum states or different bubble universes. Our best theories break down precisely where we need them most. One possibility is that the transition would be violent. The difference in vacuum energy between our universe and the region beyond could be so extreme that it would be like crossing into a region filled with intense radiation or exotic fields. You would be destroyed instantly, your atoms torn apart by the incompatibility between different physical laws. Another possibility is that the transition would be smooth. Perhaps vacuum states blend into each other gradually across transition regions, and you'd simply find yourself in a space where the laws of physics change slowly over distance. You might not even notice at first, but eventually you'd realize that chemistry works differently, that stars burn by different nuclear reactions, that the very structure of matter has changed, or perhaps the edge is impassable, not because of any physical barrier, but because the concepts of motion and travel break down there. If space-time itself has different properties beyond the edge, then notions like moving from one place to another might not make sense. You couldn't reach the edge because reaching requires a continuous path through space, and that path might not exist. The most intellectually honest answer to what happens when you reach the edge of the universe is that the question itself might be meaningless, not because we lack knowledge, but because the universe might not be the kind of thing that can have an edge in any conventional sense. It might be infinite, eliminating the edge question entirely. It might curve back on itself, making the edge unreachable. It might have a horizon that moves with observers, making the edge relative rather than absolute. Or reality might be so much stranger than our categories of thought can capture, that asking about edges and boundaries is like asking about the color of justice or the taste of mathematics. The question uses concepts that don't apply to the thing being asked about. The universe might not be the kind of entity that can have edges because it isn't a thing contained within space. It is space, and asking what contains space is incoherent. Throughout this exploration, we've confronted a fundamental limitation of human understanding. We evolved to navigate a world of boundaries and containers, edges and surfaces. Every intuition we have tells us that things must be bounded, that there's always something beyond, that space must be contained in something larger. Breaking free from these intuitions requires accepting that the universe operates by rules that violate our everyday experience. The edge question forces us to confront infinity, to grapple with the possibility that space extends forever without end. It forces us to consider that our observable universe might be an infinitesimally small fraction of what exists. It challenges us to imagine realities with different laws of physics, different fundamental constants, different possibilities for existence. Perhaps the most profound lesson is that we are trapped not by physical barriers, but by informational ones. The cosmic horizon limits what we can observe, not because there's nothing beyond it, but because the finite speed of light and the finite age of the universe prevent information from reaching us. We live inside a bubble of causality, connected to some parts of reality, but forever disconnected from others. If the universe has an edge, we will almost certainly never reach it. Whether that edge is a physical boundary, a horizon, a transition to different physics, or a conceptual limitation of how we think about space, it remains beyond our grasp. We are cosmic explorers trapped on an island in the ocean of reality, able to see hints of what lies beyond our shores, but unable to cross the waters that separate us from the larger world. The question of what happens when you reach the edge of the universe might never be answered, but asking it has driven some of the deepest insights in cosmology and theoretical physics. It has forced us to question our assumptions about space, time, and existence. It has revealed that the universe is stranger, more subtle, and more magnificent than our ancestors could have imagined. We may never know if the universe has an edge. We may never discover what lies beyond our cosmic horizon. But in the asking, in the exploration of possibilities, in the confrontation with our limitations, we find something valuable. We find the boundaries of human knowledge and the infinite questions that lie beyond those boundaries. And perhaps that's enough.